Okay, welcome to Geometry, Arithmetic, and Differential Equations of Periods. Today, Carlos Simpson, who is going to talk about the twistor space for moduli of logarithmic connection of rank 2 on an open curve. Okay, Carlos, go.
Okay, so thank you very much for the invitation. Thank you very much for the opportunity to at least virtually visit IMPA. What I'd like to talk about today is to discuss something which was part of the whole theory of Hitchin's moduli space with a hyperkã structure and twistor space and stuff like that. And then a while ago, I looked at the case of rank 1 local systems on an open curve. And so what I'd like to talk about today, towards the end of the talk at least, is the case of higher rank 2 local systems on an open curve. But before getting there, I'd like to talk about the rank 1, the compact curve case, and then the rank 1 case. The kind of the general topic here is of course a moduli space of local systems of representations of the fundamental group for an algebraic curve. And so that's some kind of non-abelian Hodge theory. And as you know, in Hodge theory, there's a notion of weight. So there's a notion of purity, pure Hodge structures, and a notion of weight of the pure Hodge structure. Then there's a notion of mixed Hodge structure, which sort of combines things of different weights together. So we'd like to see how that works with the case of non-abelian cohomology, where we think of the space of representations of the fundamental group as a non-abelian cohomology with coefficients in a group. So in the case of local systems on a compact curve, there's a weight 1 property, which we'll see in a minute. Then in the case of an open curve, you will actually sort of expect from stuff from mixed Hodge theory, you expect that there might be a piece of weight 2 in the mixed Hodge structure. And so in the case of rank 1 local systems, this was in a paper I did a while ago. And then there's a question as to how to look at higher rank local systems on an open curve, because there's some difficulties that you can see happening in the discussion, as we'll see. So I'd like to discuss how to talk about those difficulties just in the case of rank 2 bundles. So we're going to basically be talking about moduli of rank 2 bundles with logarithmic connection, and they're going to have a quasi-parabolic structure. Okay, so let's start from the classical case. So this is from Hitchin's paper, basically. Suppose we take the algebra of quaternions. Now, if you try to make a complex structure out of the quaternions, it's not too hard to see that you shouldn't take a coefficient. You shouldn't take 1 in your coefficient. So if we define kappa to be some linear combination of I, j, and k, then you can just calculate that kappa squared equals -1 if and only if x, y, z are in the unit sphere, x squared plus y squared plus z squared equals 1. So the space of complex structures is identified with the unit sphere. And then that actually has itself a complex structure, which makes it into a P1, the kind of the standard projection from S2 to P1. And the point 0 in P1 corresponds to I, the point 1 in P1 corresponds to J. The thing that corresponds to I is the point. The thing that corresponds to K is the point little I inside P1. Anyway, but so this P1 is what we would call the twistor line. Now let's explain that just in the first case, where suppose we just have a quaternionic vector space, which is to say a modulo over the quaternions. Now, if you have a quaternionic vector space, then for every complex structure on the quaternions, in other words, an x times I plus y times j plus z times k, that's going to give the action of that element on the vector space is going to give a complex structure on the real vector space V. So we get a complex vector space which will note v kappa, denote v kappa. Okay. So in other words, if you have a quaternionic, what I'm saying is, if you have a quaternionic vector space, then you have a whole bunch of complex structures parameterized by this twistor P1, which is the space of complex structures inside the quaternions. Okay. Then the construction of the twistor space is just sort of easy from this viewpoint, which is you just take the product. So just take V cross P1, and then we declare that you'll give that that total space a complex structure by declaring that the complex structure in the P1 direction is the usual one, and the complex structure in each fiber over a point of P1 is that complex structure on V. Okay. And this makes the total space into an integrable complex manifold, which is a vector bundle over P1. Okay. And then this vector bundle has sections which we'll call preferred sections. You might say horizontal sections, maybe, or something, which are just all the points of the form some vector cross P1. Okay. And it also has another structure, which is an antipodal involution. So if we change x, y, z to minus x, minus y, minus z, on P1, that's the involution lambda goes to minus lambda bar inverse. So you just throw in all possible involutions you can think of on P1. You put them all together and you have an involution. That's the antipodal involution, which sends a point of the sphere to the opposite point. Okay. And so we can think of that as a real structure on P1. It's a real structure that doesn't have any real points, but it's still a real structure. And the vector bundle that we defined before is provided with that involution by sending sigma v comma lambda to v comma sigma of lambda. So it's something that preserves these preferred sections. It turns out to be antilinear for the complex structure. Of course, as you can see here, this involution here, right? Can you guys see that? Yeah. You can see that that's antilinear in lambda, right? Because it has a lambda bar. So this is antilinear this is an antilinear involution of the vector bundle, and it covers the involution sigma of the base. So in terms of real structures, it just means that we have a real vector bundle over that real P1, over that P1 with the real structure. And then here you can calculate that the holomorphic sections of this vector bundle, which are compatible with sigma, are exactly the preferred sections. Now, the other thing you can calculate is that this vector bundle turns out to be OP1 of 1, direct sum 2 times, right? It's a rank 2 complex vector bundle because, if we take, if we take V equal the quaternions itself, that's a 4-dimensional real vector space, right? So for any one of those complex structures, it's going to be a 2-dimensional complex vector space. So this is a rank 2. In that case, it's a rank 2 bundle. And it turns out in the calculation that it's the rank 2 bundle, which is OP1 of 1, direct sum 2 times. Now, any quaternionic vector space has a basis. So it's just a direct sum of a certain number of copies of H. So it means that our bundle V in the general case is just going to be a direct sum of things of this form. Okay. In particular, it has even rank. But so what we can conclude here is that the bundle in this case is a semi-stable of slope 1 vector bundle on P1. It's also polystable, clearly, but let's just use the terminology semi-stable of slope 1. Of course, on P1, that just means it's a direct sum of copies of O1. And now you can just make a little theorem here, which is that this construction is actually sort of an equivalence of categories between quaternionic vector spaces and this stuff. So a vector bundle with a sigma compatible involution such that V is semi-stable of slope 1. Okay. So all this stuff is just kind of equivalent to having a quaternionic vector space. And the underlying vector space itself, what is it? It's the space of sigma invariant sections of the bundle. And how do you get an action of the quaternions? Well, you actually get an action of any one of the complex structures of the quaternions therefore include in particular I, J, and K, by saying, okay, this space of sections, this is a real vector space because we took the sigma invariant pieces. This space of sections maps into any one of the fibers. The fact that it's semi-stable of slope 1, you can see that that actually is going to make it map isomorphically into the fibers. Okay. Yeah, semi-stable of slope 1 plus the involution invariant. So since it's involution invariant, it means that something which is 0 at one of the points has to also be 0 at the antipodal point. Okay, and so you can see that that means that the map from V into any one of the fibers is actually an isomorphism of vector spaces, and that induces a complex structure on the real vector space. Okay, so that's how you get the quaternionic structure back. So if you have a quaternionic structure, then you construct the bundle, and you take you construct the bundle and observe that it has sigma and semi-stable slope 1 and everything. If you start with a bundle which is semi-stable slope 1 and has a sigma compatible involution, then you get back a vector space which has a quaternionic structure, and those two constructions are inverse. So that's why we say, that's why in the title here I say a quaternionic structure, you can think of that as a property of being weight 1, basically. So it's something that's analogous to having a weight 1 Hodge structure in Hodge theory. Now, suppose instead of having a vector space, we have a quaternionic manifold. So we have a manifold that has an action of the quaternions on the tangent bundle. Then we can define the twistor space of the manifold to be the product M cross P1. The complex structure on the total space is the same, which is to say, on the horizontal sections, the P1s, it's the complex structure of P1, and on each of the pieces M cross kappa, yeah, the M cross kappa here has the complex structure given by the action of that element of the quaternions on the tangent space. And there's a condition that that thing be integrable, which let's just say says that you get an integrable complex structure on the total space of the twistor space. So this is sort of Penrose's theory about twistor space of a quaternionic manifold. So if you have a quaternionic manifold, then you have this twistor space of M, which is topologically, it's a product M cross P1. So now let's go to Hitchin's paper, Hitchin's case. So remember, we recall from the Hitchin's paper about self-duality equations on a compact Riemann surface, defines a quaternionic structure on the moduli space M of local systems on a smooth compact Riemann surface. So Hitchin, by solving Hitchin's equations and so on, is able to construct a quaternionic structure, and then you can define the twistor space of that quaternionic structure. The quaternionic structure was actually a hyperkãlar structure because there's a Riemannian metric which corresponds to Kähler forms for each of the structures. For what we're saying today, we don't need the metric. You probably do actually need the metric, but so far no. Now, in this picture, if we take the complex structure I, so that corresponds to the point lambda equals 0 inside P1, then the moduli space provided with that complex structure is it's Hitchin's moduli space of Hitchin pairs or Higgs bundles on our Riemann surface X. And I was used to calling this the Dolbeault moduli space because a Higgs bundle can sort of be viewed as a non-abelian Dolbeault cohomology class, basically. Now, for the complex structure J, which is lambda equals 1, in that case, the moduli space is naturally identified with the moduli space of vector bundles with integrable connection on X. And we'll call this the de Rham moduli space and denote it by M de Rham, because it's kind of the non-abelian de Rham cohomology. So the upshot is that in this twistor space, the fiber over lambda equals 0, that's the Dolbeault moduli space, and the fiber over lambda equals 1, that's the de Rham moduli space. Now, in this case, it turns out that all the different complex structures corresponding to points which are different from 0 or infinity, that is to say, the complex structures that are different from plus or minus I, capital I, those moduli spaces are all naturally isomorphic. In fact, there's a C star action on the whole thing, twistor space, and they're all isomorphic to the fiber over 1. Okay, and this is in turn isomorphic to the moduli space of local systems, which is to say representations of the fundamental group. And so then the way I sort of learned about this was from some correspondence with Deline, who sent me his interpretation of that picture. So he gave a kind of a reinterpretation of this picture. It was kind of Witten. I mean, in the letter he says, Witten was explaining this to me and stuff like that. So it was maybe Deline plus some comments from Witten. And so we can kind of reinterpret this picture in the following way. So the m lambda. So we have this twistor space, and we have a bunch of each fiber is equal to the moduli space, but it has a bunch of different complex structures. And the idea is to say that the fiber over lambda is in fact the moduli space of vector bundles with the lambda connection. So a lambda connection nabla, that means a connection form nabla. Oh, maybe I'll write the formula is on the next slide, but it means a connection form nabla, which has the Leibniz property, but with a multiplication by the complex number lambda in front of the Leibniz rule. And so if lambda is different from 0, you can just rescale this to get a connection. So if you have a lambda connection nabla, then if you take lambda inverse times nabla, that's a usual connection. Okay, and that gives us these isomorphisms between the m lambda and the m1. On the other hand, if lambda equals 0, then a lambda connection, you have a 0 in the Leibniz formula. That just means that the operator is just a algebraic, O linear operator, and that's just the same thing as a Higgs field. Okay. And now with this definition, you can make an algebraic geometry construction of the family of moduli spaces, and we'll call this M Hodge. The reason for that terminology is that if you take this space, which has a C star action, C star acts by just rescaling the connection operator, and of course that covers the action on the affine line, and that moduli space together with its C star action can be viewed as kind of a Hodge filtration relating the Dram to the Dolbeau cohomologies. That's not, that could be the subject of talk. It's not the subject exactly. It's not exactly the subject of today's talk, sort of. But anyway, the point I'm trying to make here is just that you can construct this family of moduli spaces M lambda for lambda different from infinity. You can construct those in a way using just algebraic geometry. And then so Deline's observation is that, on the other hand, you also have an analytic viewpoint on the fiber over lambda different from 0. So for any lambda different from 0, as we saw, those moduli spaces are all the same. And they're also all isomorphic to the Betty moduli space, which is the moduli space of representations of the fundamental group. So here we're saying that a vector bundle with integrable connection is the same thing as a representation of the fundamental group. That's what's called the Riemann-Hilbert correspondence. So this, what we're saying here is the Riemann-Hilbert correspondence. So now the construction you can make is you can use that identification right here. Here we've identified a piece of this fibration with just a trivial fibration, and the moduli space involved only depends on topology. Okay, so that gives rise to what we call Deline gluing, which is you can glue this piece that corresponds to the variety x, to the curve x, by the same piece but corresponding to the complex conjugate curve. So the complex conjugate curve x bar, it just means you take the equations of the curve and just take the complex conjugate of all the coefficients of the equation. So if you think about that, you take a curve defined by some equations, take the complex conjugate of those equations. If you take a point of the curve and take the complex conjugate of the coordinates of that point, that's going to be a point in the complex conjugate curve. So there's a natural map between x and x bar, but it's not a holomorphic map, it's an anti-holomorphic map. But in particular, the topological spaces x and x bar are the same. So they have the same fundamental group. They have a naturally identified fundamental group. And this moduli space of representations is therefore isomorphic. So if we go back to the previous slide, you can see that that gives us an identification between the Hodge thing for x and the Hodge thing for x bar, okay? We need to know what to do with the second coordinate. So on the second coordinate, we apply, well, I'm not sure, this is maybe, there's a choice here of plus or minus, but basically apply lambda goes to minus lambda inverse, or plus or minus, one of those two. So we have an involution on the GM coordinate, and we apply this isomorphism on the first coordinate. And that gives us a way of gluing together these two spaces, which are, over the glue, right? Remember, P1 is glued together by two different affine lines. So then we just glue together the fibrations over the inverse images of those two different affine spaces. And you get a moduli space, which I call MDH for Deligne-Hitchin. So we get, and this way we get a moduli space over P1. So what are the ingredients that go into this moduli space? The basic ingredients are the algebraic geometry construction of the Hodge part, which is the part over the affine line. That same construction for the complex conjugate curve. And then the Riemann-Hilbert correspondence allows you to glue together those two pieces over the intersection of those two affine lines. Okay. Then if you work a little bit more, and as I said, I'm not going to give the formulas here at all because I would just get them wrong. But if you work a little bit more, then you can use the fact that x bar is the complex conjugate to x. So you can make an antipodal involution of the whole space, basically. Which you can make, so in other words, the M Hod, if you take the complex conjugate of a point inside here, you'll get a point inside here, basically. And so you can use that to relate points on one side with points on the other side. You have to make sure to get the coordinates on P1 right there and so on. But anyway, you can do that. You can do that and get an antipodal involution on this whole space. So what we've basically done here is we just used some standard constructions from algebraic geometry, namely the construction of moduli spaces plus the Riemann-Hilbert correspondence, to get to a space that looks like it might well be the twistor space, okay? Because it fibers over P1, it has sort of the same fibers as the Hitchin space, and it has this antipodal involution. And indeed, you can actually prove that this is the same. So you can prove that the space we just constructed, that's this one, is actually isomorphic to the twistor space of Hitchin's hyperkãler structure as spaces fibering over P1. Now, what we're sort of interested in for today is the fact that that you can get the preferred sections of this space also in this construction, okay? And that those preferred sections come whenever you have a harmonic bundle. I'm not going to go too much into the detail of that, but a harmonic bundle is basically a solution of Hitchin's equations. It's a bundle, it's a C infinity bundle with an operator that you would call del, one that you call del bar, one that you call phi, which is the Higgs field, adjoint of phi. And those are all supposed to be related by the existence of a harmonic metric such that the del is the corresponding connection corresponding to del bar for that metric, and the phi dagger is the adjoint of phi for that connection. Maybe I might be, well, depends on the sign of what you mean by dagger, but anyway. Then if we have one of these harmonic bundles, then we can define a point in the space of lambda connections. So for any lambda, for any real, for any complex number lambda, we can get a holomorphic bundle. So be careful, this is not the same as just E comma del bar. This is where you take E and you take the holomorphic structure of del bar and twist it by adding lambda times the conjugate of phi. And then the connection is given by, we want a lambda connection, so we take lambda times the del, and plus phi. So if lambda equals 0, this construction is just the del bar, that's the holomorphic structure of the Higgs bundle, and the phi, which is the Higgs field. Then again, there's a bit of a question about the formulas, but supposing it's extremely confusing because it's stuff about taking complex conjugates of stuff. I mean, I find that extremely confusing. So let me not try to get the formulas right here. But anyway, the preferred sections, if you get your signs right and everything, they're going to be compatible with the antipodal involution. The preferred section is defined this way. So what we're defining here this defines a family of points of the moduli space for each lambda. And you can make the same definition for lambda for the bar for the complex conjugate piece, and those are supposed to glue together. And now what we're looking for at today is the fact that how do we see the fact that we're going to have a quaternionic manifold? And the idea is that you see that in the same way that we saw that we had a quaternionic vector space. But here we just want to know how to get a quaternionic structure on the tangent space. So in view of the fact that the twistor space is supposed to be a trivialization, a product, that means that the tangent space to the moduli space should also basically be corresponding to the normal bundle of the preferred section. So the proposition is, suppose we have a preferred section like that from P1 back into the Deligne-Hitchin moduli space. And let's take the normal bundle, which is it's also the pullback of the relative tangent bundle, right? This is a section of a fibration. So the normal bundle of the fibration is just the pullback of the relative tangent bundle of the fibration. And then the statement is this thing, that this bundle is a semi-stable bundle of slope 1 over P1. And the point is that since also we have the compatibility with the antipodal involution, so this bundle also has an involution. So this is going to give us a quaternionic vector space. That's the quaternionic space, which is the tangent space of the moduli space. So the kind of conclusion of this whole theme here is that having a quaternionic structure is basically a property of having something of weight 1, which is to say a bundle of slope 1 over P1. I'm not saying that here, but you can make a correspondence where you make a Hodge structure and get a bundle over P1 by using the Hodge filtration and the Hodge bar filtration, taking the Riesz modules of those two. And in that case, there is really a correspondence between the slope of the bundle on P1 and the weight of the Hodge structure. So this is, we'd like to call this a property of weight 1. And the fact that we have a quaternionic structure on the moduli space, this comes from this weight 1 property. So let's recall that why does this seem natural? Well, because the tangent bundle to the moduli space is the H1 of something or other. And we're just basically saying that H1 has weight 1, which is in Hodge theory natural. So it's a statement about purity. Let me just comment that when you try to prove this, what's the main calculation? It's just the fact that we're actually using an H1, so it's going to be calculated by some kind of harmonic forms. Then the fact that these things are 1 forms, that's going to tell us that the transition functions that you need to pass from the A1 around lambda equals 0 to the other A1, which is the neighborhood of infinity, they're going to have a lambda inverse in them, which is going to give us this semi-stable of slope 1 property. And now what I like to say is that this is the analog for non-abelian cohomology of the property in usual Hodge theory that just the usual H1 of something is going to have a weight 1 Hodge structure. And we also have an arithmetic. Some people may be more familiar with arithmetics here. So in the arithmetic case, so suppose we have a variety over FQ, then the same property is the statement that the étale cohomology, sorry, this doesn't work well, that the étale H1 with QL coefficients has weight 1. What does it mean to have weight 1? It means that the eigenvalues of Frobenius have norm Q to the 1/2. Remember, the power of Q is 1/2 of the weight, basically, in Deligne's Fay 2 stuff. Okay, so now on to weight 2. So given this discussion of the weight 1 things, then you might suspect that somewhere or other, something is going to show up that's going to have weight 2. Because if you look at the mixed Hodge structure on the cohomology of an open curve, that has a Hodge structure, that has a mixed Hodge structure where you have a weight 1 piece and a weight 2 piece. The weight 2 piece sort of comes from the open part, comes from the punctures of the curve. Okay. Or in the arithmetic case, you can say that the inertia group has the form of a Tate twist, basically. So it has maybe a weight -2, and the space of representations of the inertia group would have some kind of weight 2 thing. So in this paper, Weight 2 phenomena for moduli of rank 1 local systems, that was from a while ago, you can find this actually is the case. So you can examine the situation. We'll look at the details in just a minute. So we find that this actually is the case for local systems of rank 1. So let's see how that works. Okay, so let's look at some details. So let's consider, so in that paper, we were trying to discuss the case of a general open curve, with an underlying compact curve and then a certain number of puncture points and so on. That induces some complications of the notations and everything. Let's just look today at the simplest possible case where we actually see the phenomenon of an open curve. So let's look at the case where x is gm, which is to say, it's p1 minus 0 and infinity. So x is just the simplest open curve that has a non-trivial cohomology. Of course, if we remove only one point from p1, then it's contractible. So if we take p1 and remove 2 points, we get gm. This has a non-trivial h1. It has a non-trivial loop in the fundamental group, which is just the loop that goes once around that c star. Okay. And now, what's a logarithmic connection? So if you think about it, a vector bundle on gm is always trivial. So if you have a vector bundle with logarithmic connection, then its restriction to x is going to be a trivial bundle. And if you want the connection to extend as a logarithmic connection on the compactification, which we'll be asking for, it really means that you can write the connection in the following form. It's going to be, so if we want a lambda connection, it's going to be lambda times just d on the trivial bundle, plus some a times the dz over z, okay? So that's just logarithmic connections on the trivial bundle on our x here that we're looking at. Now you might say, okay, that's not quite fair because you might have chosen a different trivialization. So there's kind of what we would call a gauge group here, which is you could change the trivialization, and then lambda comma a is going to be equivalent to lambda comma a plus k times lambda. One of the difficulties in this open situation setup is that at lambda equals 0, this action is singular, right? It's not discrete anymore. And I'm cheating a little bit in the discussion of this situation because at lambda equals 0, we should really be specifying the extension of the bundle rather than just saying that it exists. But let's kind of ignore that. Okay, so let's just write the moduli space in the following way. So the Hodge moduli space, it's going to be A1 cross C, where A1, of course, A1 and C are the same thing, but the A1 is used to denote, that's the variable, which is the lambda variable, which is the chart inside the twistor P1. And then the complex number variable, that's the variable A, which is the coefficient of our connection. Let's just back up a minute here, right? The A here, A is the only variable we have in this picture, just because we chose a very simple case of x equals just p1 minus 2 points. Okay. So the moduli space is A1 cross C divided by this action of the gauge group, which was what we said here. Lambda A goes to lambda A plus k times lambda. So that action is discrete over lambda different from 0, but over lambda equals 0, it stabilizes the full fiber, and so it's not such a great. So we don't really want to take this quotient. This is kind of a quotient in quotes, and we'll discuss this. We'll see this aspect showing up a little bit more in detail later. So without really saying what exactly we would like to say is the quotient, we can say we want to look at some kind of quotient here. Now, so let's talk about periods, and since we're in GADEPS, right? So the point is that how does the Riemann-Hilbert correspondence work in this case? It's just the exponential map from GM. Here, the GM is the part of the affine line, which is lambda different from 0, cross C mod the gauge group into GM cross C star, which sends lambda comma A to lambda comma exponential of 2 pi I A over lambda. Right, we have to divide by lambda because we had a lambda connection rather than just a connection. And remember, we said that if we have a lambda connection, lambda different from 0, we rescale to get an actual connection and then take the monodromy of that connection. And the monodromy of the connection is just the exponential of the period integral of this one form around the loop. Okay. It's not a gigantic period integral, but anyway, this is a period integral. And you might say what we're sort of doing is like some kind of, I mean, when we're taking monodromy of a connection, we're really doing some sort of non-abelian period integral, basically. Now we'd like to apply the same Deligne gluing principle here. So we'd like to glue this M Hodge thing to the piece to the other chart. So a chart corresponding to the complex conjugate space. Okay. Now a point, so let's use a different name. So let's use the coordinate mu to be the lambda coordinate, but for the other chart in the Deligne gluing. So mu equals minus lambda inverse. And now if we have a point inside the Hodge moduli space, which if we recall, that was this, that was this thing, right? We're also sort of ignoring the gauge group at some point here. If we have a point in the Hodge moduli space, having maybe ignored the gauge group, then it's going to have a monodromy transformation, which is e to the 2 pi I b divided by mu over the generating loop. Now, remember, we're supposed to take a topological isomorphism between the topological space X and the X bar. Of course, here X and X bar are both P1 minus 2 points. But that complex conjugation is going to take the natural generator to minus the generator because it's anti-linear. I mean, it's going to take clockwise to counterclockwise. So the Deligne gluing should actually associate lambda A with mu B whenever e to the 2 pi I A over lambda equals minus e to the minus 2 pi I B over mu. And so lifting over the action of the gauge group, right? The action of the gauge group is something which is telling us that different values of A here will give the same exponential. If we lift over the action of the, I mean, there's kind of an obvious way of lifting over the action of the gauge group, which is just to say we would like this thing, we would like this thing to correspond to this thing, okay? So if we lift over the action of the gauge group, we can just say we would like A over lambda to be the same thing as minus B over mu. And now we plug in mu equals minus lambda inverse. So that's going to tell us that lambda comma A is going to associate to minus lambda inverse comma B whenever A divided by lambda equals minus B divided by minus lambda inverse. But that's lambda times B. So that tells us A should be equal to lambda squared times B, okay? And so if you think about it, that gives you exactly the gluing condition for the bundle OP1 of 2 over P1. It's O of 2 because there's a lambda squared. Okay? As I was saying, this question about the signs, I'm still not completely sure that what's going on here is correct, but we don't care too much about that. Okay, so from the above discussion, what we can conclude is that this Deligne-Hitchin moduli space in this case, it's the total space of the bundle OP1 of 2 divided by the action of this gauge group. Then there's also going to be a natural antipodal involution, and we're going to have preferred sections. Okay. Now these preferred sections, since P1 is contractible, they're going to lift over the action of the gauge group. So they're going to lift to sigma equivariant sections of OP1 of 2. So as I said, we're going to sort of ignore the gauge group here mostly. So now remember, we wanted to look at the space of sigma equivariant sections. Let me just go back, sorry for the switching stuff here, but let me just go back to where we said that, right? In the original quaternionic stuff, right? The quaternionic vector space was a set of sigma invariant sections of the bundle. And so a similar way here, sorry about this. We'd like to look at the space of sigma equivariant sections of this thing. So if we lift over the action of the gauge group, that means we want to look at sigma equivariant sections of OP1 of 2. Now, if you'll recall here, the OP1 of 2, that I mean the space of sections of O of 2, that's just polynomials of degree 2 on P1. That's a 3-dimensional vector space. That's C3. So if we take the invariant sections, oh, sorry about sigma there. If you take the invariant sections of the real structure, that's going to be an R3, okay? Now, on the other hand, we can try to do the same thing that we were doing before, which is to say restrict these guys to any one of the fibers, okay? But the fiber is a complex line bundle, right? Because this is just a line bundle. So we have an R3 here that we're going to be restricting to a complex line bundle. So that's it's no longer going to give us a complex structure on R3. I mean, you can't have a complex structure on R3. But if you think about it a little bit, you can actually make a natural splitting of this by asking something about the action of the gauge group, for example. So for each complex structure, so for each point in P1, which is a complex structure in the quaternions, you can make a splitting, which is this R3 becomes split as R cross C kappa, okay? And the gauge group the generator of the gauge group is 1 comma lambda. So, underlying this, we really have an R3 modulo Z that we're looking at, and that's going to be R cross C modulo Z. Okay. Now, what's I feel fascinating here is that we get this extra real parameter just kind of by magic and somehow by looking at this twistor space. But it turns out that that's actually the parabolic weight parameter. So this sort of tells us that we have a parabolic weight parameter that's going to show up into the picture, kind of before we even knew that it was supposed to show up. Of course, if you look at tame harmonic bundles, I mean, and kind of historically, that the first thing to look at was tame harmonic bundles. But if you look at tame harmonic bundles, then we know that we actually do get a parabolic weight. So in this case, the parabolic weight is the growth rate of the metric, of the harmonic metric near the puncture. Because it turns out that if you take a fixed, for example, Higgs bundle, or flat bundle, and you look for harmonic metrics on an open curve, then there's a family of choices of harmonic metrics having different growth rates. One can just write this down. I mean, it's an exercise to write down the solutions of the equation for a rank 1 Higgs bundle, you might say, or a flat bundle. I mean, the Correlate's theorem for harmonic equivariant harmonic sections applied over an open curve, say, there's a whole choice of parameter, which is the growth rate of the harmonic metric at the puncture points. And that parameter is viewed as the parabolic weight. So that's just kind of a natural, I mean, there's one natural way of looking at parabolic bundles. A parabolic bundle can be thought of as encoding some information about a metric, some asymptotic information about a metric. It's the parabolic weight tells you that the metric grows like z to the p, basically. P is the weight. Absolute value of z to the p, plus or minus 1. Okay. And so we get a point inside R cross C because we also have an extension of the lambda connection as a logarithmic lambda connection. So it has a residue. And we'll call that E, the eigenvalue of the residue. And these expressions of R cross C, which depend on lambda, corresponding to a unique R3, which is independent of lambda, they allow to recover formulas, which I'll say in the next slide, for the relationship between the parabolic weights and the eigenvalues of the residue, between Higgs bundles and flat bundles, or lambda flat bundles for any lambda. So somehow or other, the fact that you show up this extra real parameter, which is parabolic weight parameter, that shows up in the moduli theory, can actually be seen as a manifestation of the fact that the monodromy transformations around the punctures lie in a space whose Hodge weight is 2. Here's the formula. So I actually gave some formulas just for the case lambda equals 1, between lambda equals 0 and lambda equals 1, and Saba and Mochizuki gave formulas for the variation as a function of lambda, which are the following. And there's a whole big discussion of things called KMS structure and stuff like that in Takuro and Mochizuki's manuscripts. But so the point that I'd like to make here is that those formulas actually, you can actually recover, wait, did I say? We can actually recover these formulas, which is to say, if you say that you have a fixed value of R3, you have a fixed space R3 that's got lots of different trivializations of the form R cross C. If you calculate what those trivializations are, and it's just a property of the fact that this R3 is the space of sigma invariant sections of a line bundle that has weight 2. Okay, an OP1 of 2 that has a sigma on it. Those are always going to give those same formulas. So these formulas, it's not just sort of an accident. Those are the formulas that you get from that picture, basically. So let's compare again with the mixed Hodge structure and arithmetic setting. So remember, if we take P1 minus 2 points, it has a one-dimensional mixed Hodge structure, which has weight 2. And the corresponding thing in the arithmetic setting is that the atypical cohomology of that space is what you call a QL of 1, right? It's a Tate twist. That Tate twist is something that has weight 2, right? The Frobenius acts by eigenvalues Q. So since weight 1 is Q to the 1/2, and Q is weight 2. Now, what about going to a higher rank case? So this is what I like to kind of say in the last part of the talk. So there's a couple of challenges that show up here. It wasn't really obvious from the paper about the rank 1 case for the weight 2 property, really what to do in the higher rank case. The first observation is the fact that we have this problem with the gauge group, that the full gauge group stabilizes the fiber over lambda equals 0. So we don't really know what kind of quotient space to take. So what we'll turn out to do today is we'll just actually look at the action groupoid, which I think a good thing to do with input because you guys are into foliations among other things. So we're just going to look at the action groupoid. But I think maybe a different possibility would be to use the definition of diffeological space. So it seems to me that probably you should be able to define this quotient as like a nice diffeological space, even if it's not a very nice sort of scheme. I mean, somehow the point of view of stacks might be good in analytic stacks, maybe a good point of view, but it doesn't really look like too much like some kind of algebraic stack because the stabilizer group, it's something which is not an algebraic group, so it doesn't really look like an Artin stack, and it's not a finite group, so it doesn't really look like a Deligne-Mumford stack. So anyway, maybe I'm just worrying too much about that, but anyway, it doesn't seem easy to get a good type of structure to go on this. The next observation is that we haven't discussed stability, and this is there's a bit of a looping problem here, because when you're looking at the construction of the moduli space of parabolic bundles over with logarithmic Higgs field or a connection or something, classically you will use the parabolic weights themselves in order to define stability. But what the project here, as you can see from the discussion of the rank 1 case, is to somehow extract the notion of parabolic weight from this construction of the twistor space. So we don't want to use the notion of parabolic straight weight itself in the construction of the twistor space, at least for aesthetic reasons, at least. So in that case, we're going to get moduli spaces which are not necessarily a finite type, but maybe only locally a finite type. So I would claim that this should be accepted as a thing, which is to say we are going to have moduli spaces that are only locally a finite type. Say, okay. Another condition, and another difficulty is the fact that, so classically when you talk about moduli of connections, for example, you might be familiar with the fact that you often like to put some kind of non-resonance condition, saying that like eigenvalues of the connection don't differ by integers or something like that. But if we go back and look at the formulas, let me do that for just a minute here. If we go back and look at these formulas, this is the formula for the eigenvalue. Well, you can see that depends on lambda. So there's no way of saying that and that's going to have two different values of lambda where it's equal to 0, for example, right? There's no way of saying that it's going to never satisfy the non-resonance. That's always going to satisfy the non-resonance condition. So we can try to impose some type of non-resonance condition, but we're not going to be able to say it's just supposed to be non-resonant everywhere. So I mean, if we take the moduli space of only non-resonant lambda connections, then that's just not going to contain these preferred sections, because the preferred sections go through some resonant points. They just have to. So we will impose some conditions, but we can't just construct a moduli. I mean, you could try, okay, let's just say the family of moduli spaces of non-resonant connections, that's going to maybe have a nicer structure and so on, but that's just not going to be good enough to have the preferred sections inside. So that's kind of the problems which we're trying to solve. And now in 10 minutes, let me try to explain what I see as sort of solutions to these problems. So now to set this up, let's look at a compact Riemann surface with a divisor. And let's just consider the divisor having only a single point, okay? And we also choose a base point, which is different from the point of the divisor. So the base point is in the open subset. We'll look at bundles of rank 2. And so what we do is we define a framed quasi-parabolic bundle with logarithmic lambda connection. So what is that? So we have a lambda. We have a rank 2 vector bundle. We have a logarithmic lambda connection. So here's where I put the formula with Leibniz rule. So it means we have, this is a bundle on a y on the compactification. From the previous slide, y is the compactification of x. X is the open variety, and y is the compactification. So E is a bundle on the compactification, but it has a logarithmic lambda connection. Lambda connection, it means that nabla of A times E is A nabla of E plus lambda times dA times E, right? This Leibniz formula term has a lambda in front of it. So in particular, if lambda equals 0, then we get just a Higgs field. And so now here's the point, which is we would like to also include a quasi-parabolic structure. And that's why I'm looking only at rank 2, because it's easy to say what a quasi-parabolic structure is. In this case, a quasi-parabolic structure is just a one-dimensional subspace preserved by the residue of this connection. And we also ask for a framing over the base point just to have a nice moduli space theory. Remember, the base point is different from y, so we're not framing over the puncture point. We're framing over some other point. Okay. Well, let's make just a couple of hypotheses here, which is, let's suppose that the framed object is rigid. That's always going to be true for connections, but for Higgs bundles might not be true, but we'll just assume that it is. And let's furthermore assume that the spectral curve of the Higgs bundle is irreducible. That's maybe going to make a couple of small points nicer. And then you can just say that there's a construction of the moduli space. But as I said, it's not going to be a finite type moduli space. It's only going to be locally a finite type, parametrizing these things, which are framed logarithmic quasi-parabolic lambda connections over A1. And I put a tilde here because we haven't made a gauge group act. Yeah. So now the point of what I'd like to say today is that you can define a gauge groupoid acting on the moduli space. And the gauge groupoid is going to consist of some partially defined operations. And this you might say is what I like to say that I think should be done here. I'm trying to maintain the hypothesis that this I think is the thing to do here, which is let's use the following operation. So we know there's a hker operation, which modifies the bundle using the subspace Fy. And I didn't write here, but there's a new natural subspace which corresponds to the kernel. Inside this kernel we have the kernel of Ey into Fy is a natural subspace. I guess no. Well, anyway, yeah. No, sorry. I guess Ey mod Fy is a natural subspace here. Anyway, the hker operation, you get a new natural subspace. We need to also include the operation of tensoring by O of y, because this hker is what some people call a down hker. So you need to be able to do an up hker. So if you want to get an up hker, you need to be able to tensor by O of y. Here you could just include down and up hkers if you like. But then we need a different operation. So this hker operation, if you think about it, it's going to sort of interchange eigenvalues, but it also does something to the space. There's a different operation we can do, which is our subspace Fy is one of the two eigenspaces of the residue. So if the eigenvalues of the residue are distinct, then you can switch eigenspaces, right? If the residue of the connection has two distinct residues, then you can say, okay, let's throw out the one subspace and use the other one instead. Okay, but of course that's not going to be well defined in places where the residue is the two eigenvalues of the residue are not distinct. So, for example, if the residue is for example nilpotent, then there's only a single possible subspace, which is an eigenvalue. Or if the residue equals 0, for example, then any subspace will do. So you can't say, go from this one to the other one. So this last operation of interchanging the two eigenspaces, that's actually only a partially defined operation. It's only defined on an open set. The idea is to put those operations together to define a gauge groupoid. And if you do that, then you actually get an atal groupoid. So it's just that the map is not proper. So if we were to be able to define some kind of quotient space, it's not going to be a separated quotient space. So if we tried to define an analytic stack or something like that, you would get a non-separated analytic stack. This is just the standard notion of morphism from something or other into the groupoid. It just means you should have liftings of morphism into the tilde space over open subsets of Z, and they should be related by gluing functions. I think you guys know how to do this. And you can even define a morphism from a groupoid into a different groupoid. I think you guys define Morita equivalents of groupoids that way and so on. Now let's do a different version. Let's do the Betty version of the moduli space. So that's going to be the moduli space of local systems with a one-dimensional subspace, but preserved by the monodromy transformation. So that's a sublocal system and a framing. And again, we have a moduli space for framed quasi-parabolic local systems, and we have a gauge groupoid. Here, the only operation, you don't need the heckas, you only need the operation of interchanging the two eigenspaces. Anyway, so you get this thing. And I just wanted to comment that what's happening here is something called, which I learned in a talk a very long time ago from Janos Kolar, and he has a paper about this, which is you have some kind of thing which is Janos called like a bug-eye space. So it's a, if you take like if you take a line and take a plus or minus one acting, classically you're going to take the quotient, you're going to get a Deligne-Mumford stack. But you could also take a different quotient, which is take the quotient just by the minus one acting, but away from the origin. That's not the same as the Deligne-Mumford quotient. That's what I think Janos was calling the sort of bug-eye quotient. And that's going to be a non-separated space, but it's still going to be smooth, right? Because it's just a smooth groupoid. It's just that we sort of throw out the point where at the origin where you have a non-trivial stabilizer. That's a little bit, that's the type of picture which is showing up here because we're using only a partially defined operation. And now the theory, we can just sort of do the same theory, which is we have a Riemann-Hilbert correspondence, which is a equivalence of analytic groupoids. So by this, it means the restriction over the open subset of P1 where lambda is different from 0. By this, it just means we take the Betty space and cross the GM. And then we also have a topological equivalence between the Betty groupoid for X and the one for X bar. And then we can use those to glue together to make a Deligne-Hitchin moduli space. And in this groupoid picture, we can just take for the groupoid, we can just take the disjoint union of these two spaces and then add in some new points which tell us how to add into the groupoid some new points that tell you how to glue those two pieces together. So you can make an analytic groupoid for that thing. Then let me just finish by saying, sorry about the slides here. We're just a few slides from the end, but should finish in 2 minutes. So, so you can also define a notion of preferred section. And maybe the salient point here, what's the salient point? Is that for general values of lambda, I mean, I need to say something here, which is if you have a harmonic bundle, then you actually get a family of extensions of that bundle depending on lambda. You get a family of lambda connections, and you get logarithmic lambda connections with a parabolic structure, not quasi-parabolic, but parabolic. For general points of lambda, the parabolic weights are going to be distinct, so that parabolic structure gives you a well-defined quasi-parabolic structure. To get from a parabolic structure to a quasi-parabolic structure, you have to pick an interval in the complement of the jumps of the parabolic structure. That tells you a bundle, and then the parabolic structure tells you a subspace of the bundle. Okay. So and modifying that interval, that corresponds to the hecka transformations, up and down hecka transformations. So that's why you get a point of the M tilde, but well defined up to this gauge group. then the other point where there's sort of a difficulty is the place where the parabolic weights might just be the same. And that's, you might say, the resonance. That's these points where it's resonant. But the point is that in that case, if we make a kind of a global non-resonance assumption that globally our parabolic structure, comma, parabolic, comma, eigenvalue, if that globally is not equal to 0, then at a point where the parabolic weight is 0, then the eigenvalue has to be non-zero. So that means that in that case, we're at one of these points where you can do the flipping operation between the two eigenvalues. And in that case, you just choose one of those two subspaces, and you don't care which one it is. And the P operation interchanges those two. So sort of at points where you have this resonance problem, you just say, okay, if I had a resonance problem for the parabolic weight, then on the other hand, the two eigenvalues are going to be distinct. So I can just choose one of those two eigenspaces. That gives us a well-defined point of the M tilde up to the gauge group point. And then let's see that. Let me just say the theorem here. So the theorem is that if you can define a moduli space that way, then the weight theorem says that the normal bundle of the preferred section is a mixed twistor structure. So it has a weight 0 piece, which is the change of framing. It has a weight 1 piece, which is the deformations of things that preserve the monodromy transformations at infinity. And then it has a weight 2 piece, which just comes from the rank 1 weight 2 discussion that we had, which is the weight 2 piece corresponding to those monodromy transformations at infinity. So that's what I wanted to say, just to comment that the proof of that theorem, you need to use this theory of mixed twistor demoduled by Saba and Mochizuki. And in fact, I said theorem, but actually this is kind of still work in progress to extract that mixed twistor structure statement from the general theory of mixed twistor demoduled. So that's a little bit still in progress. Okay, so I'll stop here.
Okay, thank you.
Okay.
Any question? Maybe, well, I first stop recording and then